Good evening all, and welcome to tonight's TI Technology webinar hosted by Texas Instruments Australia. As you can hear by my voice, I'm excited and I hope you are. I'm bringing you tonight STEM with Jim Lowe and Peter Fox. My name is John Baymont and I teach mathematics to years 7 to 12 students at Lachlan Catholic College, Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I'm excited to introduce our first panelist this evening, Mr. Jim Lowe. Good evening, Jim.
G'day, John. How are you? G'day, Peter.
I'm very well, my friend. Thank you for joining us this evening. As you can see, Jim is a very experienced and knowledgeable maths educator who is always willing, and I have first-hand experience of that, to support his fellow teachers and students either in the classroom, through QAMT, or at conferences, or at UMe Deadly, which is a fantastic initiative. So thanks, Jim, for joining us this evening.
Thanks, John. Looking forward to it.
Our second panelist this evening is the young man, Mr. Peter Fox. Good evening, Peter.
Good evening, and thanks for the young reference. I'm not sure that it's appropriate, but thanks anyway.
We won't tell people that photo was taken 20 years ago, Peter. It's okay. As you can see, Peter now works for TI Australia, but was a maths and physics teacher for 25 years. I know he is very knowledgeable with all forms of TI technology, especially the computer algebra system, or CAS for short. Has been spending a lot of time recently on Innovator and STEM projects with TI, so I'm excited to hear what you've got to say tonight, Peter. Thank you for joining us. And no further ado, I know that really what everyone would like to do is to learn a bit more about STEM and to see what these fantastic TI educators in Australia have got to share with us. So, Jim, I will be passing it over to you.
Thank you very much, John. And sharing my screen. That will hopefully be coming up for you. And
fantastic,
so,
Jim. We can see it very clearly. All yours.
Okay. So, for this evening's webinar, and a very broad topic such as STEM, I thought I'd try and encourage people to get into this area by looking at a very, very simple application, or at least I hope it's simple, and to show you where you can get some support to do these sort of things. So, as was available on the website, this is the overview of the session we're looking at tonight. Because it's National Science Week, looking at some of the free resources that are out there, how you can work like an engineer using technology such as the TI-Innovator Hub with your Nspire or your 84, and throw in a little bit of coding for good luck and see how we get on. Now, the whole STEM, I hesitate to say debate, but the discussion about STEM education and where it's heading, there's all sorts of different things. Some schools are running special STEM classes, others are just trying to incorporate STEM activities into their maths classes. Hopefully I've got an activity this evening that can go either way. If you've got an integrated program, then it's got a number of different aspects that you can include, but it's also something that you could do wholly within a maths class to give it a STEM context. So let's have a look and see what's going to go. We're going to look at building an electronic dice, or maybe an electronic die if you want to be particular, but I have it on good authority that dice has been accepted as singular and plural for quite a number of years now. So there's a few little steps in there. We're going to build a simple circuit using an LED. We're going to write some code to turn that on and off. We're then going to duplicate that to make our multi-dotted display for our dice. We're going to modify the code, and finally we're going to generate some random numbers and send those random numbers to that code, and hopefully turn them on and off in the right order. So unfortunately, with the setup that I've got available tonight, I can't quite make this thing go live, which is unfortunate. Hopefully in another webinar soon we'll be able to, or I'll be able to do that. And my wife will be very pleased because it'll force me to clean up the mess on my desk if people are going to see what's going on around me. So let's get into this and look at using the TI-Innovator and this idea of a breadboard. Now, a breadboard is a thing that's been around in hobby electronics for years. It simply allows you to plug in electronic components, and as you can see from the picture there, join up using little link cables, just plugging them into the holes that you see here, and you link them up and you get a circuit and you can make things happen electronically. So in other words, it's taking the need to solder out of the equation. So there's our first point, coming back to, we said how easy it is to get into this sort of thing, so we can take the need to set up soldering stations in your classroom out of it. But should you wish to go into that, that's a relatively simple thing to do. Now, a few of our webinar sessions have looked at the Innovator, and a lot of them have looked at using the various lights and sensors that are available on the hub. But we're going to use this little breadboard interface, a series of pin slots here that we can use to connect between the Innovator and our breadboard. Now, a lot of this information is available on the TI website, and let me just change over here and we can see that on the website we've got our TI codes, our 10 minutes of code, and you can find those for the Nspire, you can find those for the Innovator Hub, and also for the TI-84. But if you hunt around, you can also find Path to STEM projects. And you can see here, you can do great projects like build a little speaker or make a switch from a banana, and why, as if you would. You know, I don't have to list them there. You can see them there and you can check them out on the website for yourself. But what I wanted to point out, that it's in terms of building skills, either as an educator so that we can do this with our kids, or for the kids themselves on here, as well as the project, it's important to look at the topic here that's setting digital output. So if we build a speaker, then obviously sound is our digital output, but what we're being told and shown in this video is the basics of setting output via this breadboard. And so you use this as not a one-off, but as a starting point to do different things. And if I jump back to my PowerPoint here, you'll notice that this is a screen grab from that video in that first one talking about how to build a speaker, but it includes basic setups for the breadboard, and you'll see here using an LED, and that's all that I'm going to do tonight, is use a simple LED to represent one of the points on a dice so that we can build our electronic dice to show the random numbers that we've generated. This PowerPoint will be available, so if you can't find it on the website by searching or browsing, the link is there that will take you to those STEM activities. Okay, so what have we got when we get into this thing? Well, you can see on a breadboard, a little bit fuzzy picture there, but the wire's nice and focused. But we make connections. Now, the idea at this side is that these rails that run down here on the outside are all connected. And these sections along here are also connected. And so what we've got in this picture is that you'll see that blue wire going over to our hub. It's going into there. One pin of that LED is into that same row of pins there, so we have a connection via the breadboard between those. Our LED comes over to here, and then we have a resistor in there so that those two pins are now connected. The resistor plugs in there, and we've got another pin going from there back to our hub so that we've got a complete circuit. Right? And that's as simple as it can be, really. It's plugging in, and if it doesn't work, you haven't soldered anything, you haven't got those hassles. It's nothing to do with your soldering. You can just pull it out, test it, turn it around, see what's going on. And that's really great for the kids, because if you don't have experience with electronics, you'll realise that an LED will only work if it is in the correct orientation in the circuit. And so, you know, they plug it in and it doesn't work, take it out, turn it around, test it the other way. And so it's really easy to come up with that circuit. So now we've got a circuit here. The resistor is there really just so that we don't have all the current that's available going through that LED, just to, if you like, slow things down a little bit. And then two things about this breadboard connection. In order to test what's going on there, so in order to test this circuit, we want some current flowing through there. Now, we haven't written any code or anything like that at this stage, so it's really easy because you have a power source there. So you'll notice that that pin is going into 5 volts, and the blue wire going into the ground, and so the hub is providing 5 volts through that circuit, and hopefully, got ahead of myself there, sorry, thought I had another picture in there. So that circuit that we've got there would be working. There is a faint glow at that bulb, so that I know my circuit is complete. And then we can take the kids on to the coding to turn that on, and we're sort of separating the two parts so that you're not trying to work out, is the problem with the student's code they've written, or is the problem with the circuit because they've got things connected the wrong way or whatever. So we get the circuit working first, then we go and write some code. And as I said, that will give us the power and run the circuit. When we're ready to go and write some code, we simply remove that wire and plug it into one of these ports at the top. Okay, so, and since we've only got one of them, I'm going to plug it into port 1. So exactly the same circuit, but we're now going from port 1 through that circuit to the ground. And that will only turn on then when we write some code to actually turn on this output. Now, you'll notice that I've also disconnected the power lead there simply so that you could see that lead. So it would need to be plugged in order to do that. So that's the first part. And then, of course, once you've got the breadboard circuit working, we now know we can go and connect these things up, and you can see that's the most dodgy job there of ever. Those wires are just twisted together, no solder or nothing, but exactly the same connections as we had before, and we've got that LED lit up. So, you know, once you've done the testing with the breadboard, that's basically the circuit. We can hook that up, and then, if you like, get the soldering iron out and connect those. And then, because we want to make our dice with the LEDs to light up as if it was the face of a standard dice, we're going to make 7 of those and then start hooking them up. Sorry, John, were you going to make a comment there?
No, I'm
saying
that's the only great bit of welding job going on there, Jim.
Yeah, Not to worry. Okay, I've done worse than that sometimes. Yeah. Okay.
The good thing for the kids, though, is that at least if they, you know, they learn different ways to make those connections and realise how some can be better connected than others, and how soldering is so important to make a solid circuit for themselves. They learn from those areas.
Nothing worse when kids are learning to solder if they've got a dry joint somewhere that's not letting current flow. And so, you know, they can test it in different ways and forms and so on. And obviously, I got that to work, as I said, cut a lead in half so that I could join it on, the resistor, the LED, and then the other half of the lead so that I could plug it in there. You know, it's those sort of things it's really easy to set up in a classroom. A packet of those from a place like JCar, you get 25 or more for a few dollars sort of thing, and a few resistors. It's not crucial what resistor it is, but, you know, there's some guidelines on the website as to what you can use. And so when we get to this point of coding it, okay, that's what we're going to try and set up. So we're going to have these 7 LEDs, and you can see that, you know, if we randomly roll a 1, we're going to light this one up as we would on a dice. That would just be the 1 dot. If it was a 2, it would be these ones. 3, we're going to light, oops, I just spotted, yeah. Of course, that one should be numbered 6, okay? And we'd have 1, 6, and 7 lit up if it was a 3. If it was a 4, it would be 1, 2, 5, and 6. If it was a 5, 1, 2, 5, 6, and 7, and so on. Right? And finally, if it was 6, it would be 1, 2, 3, 4, 5, and this one that should say 6. My apologies for that. And so when we do the code, again, I'm sort of trying to get across this whole STEM concept here, that we can do the testing of the circuit and the basic circuit on the breadboard, and then we can go and write some code to turn that on and off, and that's actually explained in that video, getting digital output. But can I have a little bit of a look at that now, if I can get to my screen? And there's a whole other bits and pieces in there, but you can see that, you know, we're going to connect what we've called LED 1 to BB1. Fairly self-explanatory. You think back to my photos there, we're going to connect one LED that we're referring to as number 1 to that first port on the breadboard. And likewise, you know, we're going to be pretty logical and connect LED 2 to BB2 and so forth and so on. And if I can just find it in there, that's what we're referring to there. So breadboard 1, 2, 3, 4, 5, and we just get those little pins and plug them in there and so on. And so that's what we're referring to. We could complete each circuit with, you know, make it individual, but we could also join them all together and just have one ground coming back to the breadboard. So that would work fine as well. Okay, let's go back to our code. So that's the connection, and then the instruction that's explained in the video is to simply send a command to set a particular LED on. And at the end, we set a particular LED off. It's fairly straightforward. So just swap back there to, where am I? In there. No, that's not what I wanted. Didn't want to do that. Let me get back to where I want to be, the PowerPoint. Okay. So the sequence that I said I was going through there, we can test each one of those little circuits individually, right? by just doing that. Connect it, set it to turn on, set it to turn off, and I scrolled through fairly quickly there. You might have noticed I had a wait command in there to let it just stay on for 3 seconds. Now, there is probably many different ways we can do this, but I decided that I would set up lists to work out or to control which LEDs would actually be turned on given a particular roll of the dice. And so we're going to set up the list, turn on the required LEDs, and then finally turn them all off again. So that's what I had in there. And now you'll notice that that seems a bit repetitive, and those that know a bit about coding are probably thinking, well, why hasn't he got a loop around that? Why not simply say, you know, for I equals 1 to 7, set LED I off. And Peter, you might have an update, but the last time I went through all the manuals, it wasn't possible to put a variable in there. It had to be actually a constant to address the ports and so on. Is that still correct?
Yeah, that's the easiest way to do it at this stage. There are other commands we can use. Rather than set LED 1, we can do digital, or if teachers really want to get adventurous, you can connect up a integrated circuit to it and use a clock pulse and basically send binary data down into an integrated circuit. So you can get really fancy, but what you've got in front of you, yes, is the simplest way to do it.
Yeah, and that was the purpose of this one tonight, is just to give you a very, very simple introduction into how you could get into some of these STEM projects. And I'm sure teachers out there watching this would be thinking, well, instead of turning an LED on, I could turn, you know, all sorts of electronic components on and off and so forth and do these things. For what it's worth, I set it up that this program DICE would get a particular value that I called V set to it. So obviously I would have a program that would be generating my random numbers. The random number would be stored in V and passed to this program here that we called DICE. So if V was 4, then this program would light up the LED pattern for a 4 on the dice, so the 4 corners would be lit up. And so, whoops, scroll too fast. They're way too fast. So if V is 1, then I only want that central dot to be, or LED to be lit up. So that's it. V only gets LED 7 turned on. If I want 2, I want 1 and 6, and so forth, 3, 1, 6, and 7. And you can see the pattern there, and so on. So that we set up this list called ON that tells us which LEDs have to be turned on. And we've got that in a nested if statement, and we connect the LEDs to the breadboard. That could have been, that could be before that, but it's got to be in that initial part. And then again, because we can't pass the variable to the LED, this is how I got out of it. If I equals on I, so in this loop, I is going from 1 to 7. So if I is 1 and it equals the value in that list, and I is 1, then we set LED 1 on. I need this little bit here to decide that, whoops, scroll too far again. I need this little bit here because I can't, to decide which statement to operate here, so that I can't just put the value I in there. So it's a little bit messy, but it works, and we can turn things on. And as we said, we then wait for 3 seconds and then turn them all off again, and we would return back to our main program that's generating the random numbers and have the kids whatever method they've got in the program to generate another random number. So unfortunately, it's not terribly interactive, folks, but hopefully, as we said, we've kept it very, very simple so that you can get the idea that with a few basic commands, you can get the kids into this STEM world of designing something, building it, and you can see that that could be built out of, my first one was a bit of polystyrene just for the LEDs poked into the through the polystyrene and the soldering done at the back of it. We intended to do a few more fancy ones and getting them to drill some holes in plywood and cover it with a bit of perspex so that it would light up behind the perspex and so on, which could be an industrial design project to build the whole thing. We can go into a bit of physics about the circuits and the resistors and so forth. So it's got potential to grow there. But I just wanted to emphasise tonight that it is really simple just to get into it. It's not hard with the breadboard to go experimenting with these things. And as we've said, those two commands to connect to the ports on this hub and then to send on or off commands to turn devices on. That's all it took. So it's a very simple little bit of coding, and it's all explained in there on that website, as I said. So since I can't make it any more interactive, I think I might finish up there, John, and just encourage people that, go out and get hold of one of these hubs and a few electronic components. I just went down to JCar and, I'll have a bag of that and a bag of this and a bag of that, and went home and played and so forth. And you can see my next trip to JCar is to get a new tip for my soldering iron so I can actually tidy up that thing. But I will leave it there.
Great, thanks, Jim. And I think that the point that you're trying to make there as well is it is so easy, especially with the support of the TI website, which I sent links through earlier to do, and it really addresses the technology and the engineering side of the STEM mindset that I feel that a lot of projects are missing. A lot of them are addressing the science and the mathematics, but I really feel that the Innovator Hub really starts to allow us to access that technology and engineering and combine all four together, so it's quite powerful, isn't it?
It certainly is. And, the first attempt we had at doing that, after the kids got the first one going, they then tried to create the whole thing on the breadboard. And if you can imagine 7 LEDs and 7 resistors and connectors to all of them, then it got messy and it suddenly became clear, okay, that was the design part. We only need to test one circuit. Now we just duplicate it without the breadboard. And so it really had an element of design and almost manufacturing and thinking out what's the best way to produce this thing, So I thought it was quite good.
That's right, and we don't have to be the experts. I think it's really important that we reiterate that we don't have to be experts. Not only the website, but also kids don't actually, in my experience, the kids don't come to me and say, how do I do this? They go off and try and find it themselves. It really is a shift, and that leads a nice little segue onto somebody who is an expert. And Mr. Fox, we can see your screen, so we'll pass over to you.
Thank you very much. Just letting viewers know that there's no interruption in the signal. It is supposed to say National Broadband Network. I think it's a nice area for students to study as a part of a STEM package. It's one of the biggest expenditures on a single project that our government has done for those Australian viewers. For those international viewers, we're playing catch-up. I was going to say catch-up football, but I'm just going to leave it at catch-up. So the idea of the National Broadband Network, it has so many little sections that you can spin off and study, and some of it relatively easy. So what I thought I'd do is provide a bit of an overview, because I was surprised at how little students actually knew about how this stuff works in terms of even just the big picture. So what we're going to do is start with how do we convert text into numbers, and there was a code set up years ago called the Ascii Code, and we still use it. And we're not just talking about sending a text message from one phone to another. No, we're talking about anything, because people need to understand, or students need to understand, that whether it's a website, whether it's an image, it's basically a mixture of text and numbers. Websites are essentially a bunch of text, HTML code, that sort of thing, that gets sent down a wire. It used to be a copper wire, and that's all about to change into optic fiber cables. And then how do we get that number, which is an actual Ascii code, and I'll show you Ascii in a minute. It's not hard, it's pretty easy. How do we get that decimal number and convert it into binary, and why does it need to be binary? And then the next bit is we convert that binary number, which is just ones and noughts, into a flashing light. And why is it important that it's coloured? That's where you can bring in some of your science, the fact that red light bends by a different amount than green and yellow and blue and so on, which allows us to put 1,000 signals down a single optic fibre where we would have only had a single signal going down a copper wire. So that's where the big advantage is. And for the physics people amongst you, you might want to think about this, and that is light travelling through an optic fibre cable actually travels about 1.5 times slower than electricity running through a copper cable. So technically, the optic fibre network runs slower on the basis that the speed of the signal is slower. However, the best analogy that I could come up with is, imagine you've got a 500-lane highway where you can travel along at, let's say, 70 kilometres an hour, compared to a single-lane highway where you can travel along at 100. It's very rare that, particularly once it starts to get congested, it's very rare that you're going to be able to travel at 100 kilometres an hour, where on your 1,000-lane or 500-lane highway, you're going to be able to travel along at that speed quite frequently. It's going to be pretty rare that that gets clogged up. So that's the best analogy there. And then finally we send this flashing signal down an optic fibre cable, which is again where you can bring in some basic Year 9 science, where we talk about total internal reflection. Why does the light get trapped inside the fibre? And having done that with students, just putting an optic fibre cable up against a flashing light and the kids seeing it flashing at the other end, their eyes just glazed over and like, how does that work? How does that happen? And I like it when students start asking things like why and how. So that's what happens on the sending device, and there's one of the most important steps is the first one on the receiving device, which is how do we get that flashing signal, that light that's going off and on, how do we receive it? Well, on the Innovator it's pretty easy. There's a light-dependent resistor, that's what LDR stands for, and that's going to capture the light and turn it into a messy number, but then we have to decide, does that messy number become a 1 or a 0? And once we've made that decision, then we convert that signal into binary. So we get that messy number and decide at what point does it become a 1 or at what point does it become a 0. And suddenly we have 1s and 0s back on our receiving device, which we can then convert back into decimal. So we're undoing everything that we did and get that decimal converted back into text. All right, so let's make sense of all of this. The first thing we're going to tackle is this text converted into numbers, this Ascii thing. So let's have a look what it means to convert text into numbers. This Ascii table that you see in front of you was developed quite some time ago. There's no exam at the end of this webinar, so you don't need to memorize it. That's the good news. But the better news is your calculator knows it. It's built in, like any computer knows it. This is how it works. So let's see how we can get this sort of stuff brought up on your calculator. Well, the first part is we're not at this stage interested in all the stuff on the left. I just want to draw your attention to the text on the right. And there's some beautiful patterns even just in the text. I know it doesn't seem beautiful yet because it's in decimal. When you put it in binary, the elegance of it is very, very clever. They did some thinking about this. So here's what I want you to do. If you have a calculator in front of you and you're on a calculator application, you can type in the word ORD, put some parentheses there, and you have to put in quotation marks because we're putting in some text, and put in ORD with the quotation marks and T, and see what you get. I'm going to bring up my calculator. So if you haven't got the benefit of having one in front of you, let me try it. So ORD, put some quotation marks in there, and we get 84. Let's just go back to that ASCII table and have a look at the number 84, and there it is, capital T. So this ORD command returns the ASCII code, which is pretty useful for us as we move forward. If you're doing this with students, there's nothing wrong at the early stages getting them to write their name in numbers, which we'll have a look at in a minute, how we can do it quickly. But without doing the programming, can you write your name as just a bunch of numbers? Then get them to convert those decimal numbers into binary, all by hand, and make their numbers as ones and noughts. And talk about how that might look in, well, I used to do it as a CD, but apparently that's old-fashioned now. So there's T on the calculator as an ASCII code. Let's have a look at another one. We wanted E as well, and lowercase e, so most people are probably betting that that's going to be 69 and 101. Let's have a look. So I'm just going to go and pinch the command and put it back in. And again, with lowercase e. And if you haven't picked up a pattern yet, let me give you a clue here. And we'll do another one up here. Probably should have done it the other way around, but I think most of you are maths people, so you won't mind. They're 32 points apart, and that's not coincidental. And as we look further into the binary number system, that will become more and more obvious as to why they're 32 units apart. So there's a command you might not have known that was on the calculator. So now that we have the ability to turn a letter into a number, we might want to have a look at things like how do we get a whole word rather than just a single letter. So in your honour, John, I thought let's convert your name into a bunch of numbers. So
Thank you very much,
John,
my friend.
there. What was that, sorry?
I said, thank you very much. Very kind of you. You could have just said that you chose a generic name that, is quite general, but thank you very much. You don't, sort of honoured it to me.
Thank you. Not a problem. All right, so let's have a look, see if we can convert John's name, at least his first name, into a bunch of numbers. Now, the next thing people are going to go is, how do we find all these commands, this odd, character, left, mid, these sorts of things? Well, I'll show you that in just a moment too. So let's start with this left thing. So we'll go back to your calculator application, and if I type in left of something, you can see it's actually recognized by the calculator. So I'm going to start with saying W is going to be equal to, and you'll notice I put in quotation marks. So if I want left of W, and I'm going to try 1, we get J. And I'm pretty sure people will be able to guess what that's going to do. It was either going to return O or it was going to be JO. So obviously the bigger the number here, the more parts of John that we return. That would be useful if we could just get one letter. So in other words, we could progressively go through the whole name. We also need to know how big the name is. There's a really cool command called dim. And that's not saying you're dim, by the way, John. We just want to find out what your dimension is. And it says it's 4, which essentially means that there are 4 letters in John's name. So that helps us decide how big a loop might be if we're going to automate this whole process and start looking through and picking out the letters in a text message, which could be 100 characters long. We want to convert all those 100 characters into numbers, then into binary, which is huge, and then send it to the flashing light. Now, the good part about this, when I've done this with students, I get them to read the code manually, and anything faster than 1 bit per second, and they make a lot of mistakes. Even at 1 bit per second, they can make mistakes, and they develop some sort of an appreciation for a computer that talks about megabits per second and doesn't make mistakes. At least they're a little bit more friendly towards a computer when it's reading megabits per second and there's one letter wrong, which in itself very rarely happens. So before I go into doing the mid thing, let me show you over here where we can get this stuff. So I've just hit the catalog. You'll notice on the catalog there's all these different tabs. This one here, the first one is like an alphabetical listing of everything, which is useful, but if you don't know what you're looking for, I know that sounds silly, but if you don't know what you're looking for, this second one's very handy. So you'll see one of the options down here is string. So we can convert to string, we can get a string dimension, and if I click on it, you'll see that's just dim. It's the same command that you would have checked any list. Concatenate is a lovely one that adds two strings together. And here's the commands we're looking at now, left, mid, and you'll see that mid has this extra bit which we're going to use. There's right, which is the opposite to left, and if you don't know which is which, then we've got more problems. And there's this string format, there's character and numeric code. So it's put it in language for us. That's that ORD thing that we had before. That's what returns the Ascii code. So it says numeric code. It could say Ascii code. All right, so let's go back here. The other thing we wanted to look at was this mid command, which you're going to find is actually very useful. If I put mid 1, that's not very useful. What about mid 1, 2? I wonder what that does. What about mid 1, 1? That looks very much like our left command. So let's experiment with some of the other number, this one here. And this is where we start to get some useful stuff. So here's the trick. If we want to strip an entire name apart, we need to know how big it is, in other words, its dimension. Then, once we know that, I know that John's name has 4 characters, so I can strip each letter off one by one. So if I did that step by step here, let me just paste that command inside, and then we'll paste that one inside, and I'm going to do it a different way this time. So there's your name in numbers, John, 74, 111, 104, 110. And of course the 74
sounds good to me. Yeah.
The 74 would have been a little bit different if we'd used a lowercase, but here are a proper noun, so we used a proper noun to do it. All right, so
I noticed there, Peter, that you're using I noticed you're using the CAS version of the TI Nspire. I presume that all these commands also still work on the non-CAS version?
They certainly do. In fact, it was the non-CAS version that reminded me to a certain extent that you have to use quotation marks because it spits back and says it doesn't know what W is, and that's where you've got to be careful. You can store a string, as you'll see on the screen now. You can store a string in the CAS and non-CAS version. So everything I've done here will definitely work on the non-CAS version because there's no algebra being executed. It's all just text, which it does very well.
Now, I know that obviously on the TI-84 we can use variables and we can store variables, and we can still do the coding like much of the Nspire, but I presume we can't do this on the 84?
Yes, you can. Some of the commands are a little bit different. Some of them are actually easier. So, for example, now I've got to remember whether I think it is even the same augment command is the same. Instead of using assigned equals to that you can see on the screen now, you use the store command. You don't have to do the introduction like I've got up there, data T and data N. I've made them into a matrix, a list rather, whereas you can do that much easier on the 84. That's an easier process. Or you can just use list 1, 2, 3, and 4 because they're built and ready to go. So in actual fact, you can do it with less code than what you see here on the 84. So it's a little bit quicker. And you can also do what you're going to see later on, where you can compile lots and lots of programs together. You can do that on the 84 as well. Highly recommend it.
Awesome. Great.
All right, so let's have a look. The first part that we'll have a look on here is this idea that you can request a string. So that first part of the program, enter your word and we'll type a word in and it's going to be stored in W. And then the next part of the code basically says, well, how big is it? That will tell us how many characters are in our word. Then we start this loop, and essentially that loop is what you saw me doing on the screen before, where we're going from a 1 up to whatever the dimension is. In John's case, it was 4, so we would go through this loop 4 times. And you can see that all we're doing is changing this value here, this I in the middle. That will start off at 1, then 2, then 3, then 4. That's what you saw on my calculator screen before. So what do we do with that value of t? That goes into what I've called data t and data n. Now, I could have done it in one hit. I could have removed one of these commands, but I thought I'll do it in 2 steps. So data t is the actual text. So what that will do is just give you a list full of all the letters. Then the next one is turning it into a number. That's that ORD command that we used before. So data t is a text and data n is for our numerical values. And then just for fun, I've got it to show them at the end of the actual program. So let's have a look how that program actually works on the calculator. So after the webinar, I'll put these files up on the web. And here's our program that you saw on the screen. There's one more line, this local D, I, and T. All that does is mean that rather than cluttering up the calculator with all these variables, it only uses them in the actual calculator program itself. So we're going to run this text to number thing. Let me just clean up that space now. So you see there's lots of variables being created here. So we'll run this text to number program. And there's John. And you can see it's separated them in our data text list at the top and then turn them into numbers at the bottom. We could run it again and we'll put Jim in there. So there's Jim's name in numbers. Not surprising, it's got the same number at the start. And we'll do one more. We'll put in a slightly longer one. So it's handling it. It's figuring out the dimensions or how many characters in our list and then spitting them all out as numbers. So the next thing we really need to do is get those decimal numbers and turn them into binary numbers. So decimal and then convert it to a binary number. Now I know there is a command on the calculator that does it. All right? And when I did it before with students, we actually used that idea where we'd use the command on the calculator for the students to learn or self-teach, flipped classroom approach, how to convert a decimal number into a binary. Let me just show people where that is on the calculator. So the number 80, for example, capital P, if we go into our catalogue, you may have noticed before we've got all this string stuff here, but we also have this nice command that says base. There it is as binary. The only problem is that's not particularly useful because I want the individual characters. I want 0 to turn a light off and 1 to turn a light on rather. And we can't strip those digits out of there. So we actually have to do it bit by bit, literally bit by bit. So here's our binary numbers. So if people haven't seen these before, you can have the students just get the calculator to count through a loop and display each number as a binary result. Put a little wait command and the students will actually start to see the patterns. They see that as soon as you get a 0 or a 1 rather, it carries to the next digit. Get another one, then it carries to the next digit. Then of course there's the patterns within that we see that the powers of 2 coming up, so we can see that's our 1s column. The next digit is our 2's column. The next digit is holding our 4's column, then the 8's column. And here's the bit that kills me, is that we had Roman numerals in the curriculum for so long as a number system, and they never put binary in as a number system. However, it is included in grade 5 mathematics in Australia. I just don't know of any year 7s that have been taught binary numbers in year 8. I would be delighted if there are some out there. So here's our simple
My
program.
students have fit, if that's any consolation, Peter.
Oh, that's good. So therefore, a sample of one out of how many schools so far? It's a bit disturbing. So look, here's our simple program to convert a decimal number into a binary and drop it into a list. So I've called this list, there it is to start with. I use the dimensions of our data n, that is the numbers. I want to know how many numbers do I need to convert. So that's equal to D. And then our next step in the program is to say, well, I'm going to run through this loop D times. So I've got D numbers to convert. But we need a second loop to do it, because our second loop, which is coming up here, is the bit that converts each number into an 8-bit binary. That's why it's for j equals 1 to 8. I thought people would like that because it's a j, like integer. So v is equal to int n over 2 to the power 8 minus j essentially says, well, if I divide some number, and let me show you what it's doing, if I had something like 80 and I divide it by 128, and we'll do approximately equal to, we get a number less than 1. Of course we do. Then when we go to our next power of 2, our next lowest one, 64, then we see that we'll get a 1. Well, 1.25. We're only interested in the integer part, so in other words, we return a 1. So the first one, the 80 would have returned a 0 because we're looking at the decimal, whole number component of it. And then in the next one, it would return a 1. Then what we do is, because it returned a 1, we strip off 64. So we'll go 80 minus 64, and then we'll start dividing that number. We'll divide it by 32, which of course is going to be smaller than 1, therefore we'll return a 0. And then we'll divide it by 16, it will return a 1, we'll strip off the 16, and so on. So let's have a look what it does. Oop, my computer wants to update. Should I do that now? No. All right, so here's our decimal to binary thing. And, oh, very nice, John. Yes, 10 types of people in the world. Very good. I like that. All right, so decimal to binary. And what it's going to do is nothing. Well, that's not quite true. It actually created a list. And if I look on my list here, data binary, it created a list. So it converted my first name, Peter, converted into ones and noughts, which we would use to drive an LED and switch it on and off. That's the concept that's happening there. So it's created its own little list. It didn't print anything out as it went. You can see here it's just storing them. Data, B for binary, and it's just checking to see if it's got to store a 1 or a 0. Remember, V was either going to be a 1 or a 0, so it's storing the 1s or 0s. That's it. So our last step, when we come back here, is to get those binary numbers and put them into a flashing light, which we can choose the color. Now, if you're using an RGB diode, which is the red, green, blue, you can run out millions of different colors, but just bear in mind that optic fiber cable can only detect a certain number of colors. So that's worthy of keeping note if you're actually using one. And the little splitters that convert them and separate them back into their component colors as it travels as white light down the international superhighway. Those things are a couple of $1 million each, those little splitters. So just in case you want to buy one to take it to school, might want to put in for a big submission on that one. So here's our conversion going, and I've used the digital out just to be different this time. So I've said connect digital out 1 to breadboard 1. Now I have got a webcam set up, but it doesn't want to show the picture, but it's essentially what Jim had before with just a single resistor going through a diode to make a light flash on and off. So here's the simplicity of the code. The first part that we're looking at is just to tell the calculator we're going to talk, or the innovator rather, that we're going to assign digital out 1 to a breadboard output. So it's either on or off. The dimensions of the list, So we've converted into binary, so we need to know how many times we're going through this list, how many ons and offs do we need to generate. And then that essentially says, well, that's how many times we'll go through the loop. And then the simple part of it says, if that bit, that data bit is a 1, then I'll turn the breadboard output on. Otherwise, it must be a 0. It's binary, it's either 1 or 0. So if it isn't, then I'll put it off. And that's it. And when I run that program, it'll actually generate lots and lots of 1s and noughts on the actual calculator and then put that and turn the little LED flashing on and off. So, where to next? If you remember that first slide, we talked about the 3 or 4 steps that we need to do. And here's the bit that a lot of teachers may not realize. This is kind of like the piece de resistance before we head into the hard stuff, which I'm glad to say you won't have to do too much of. So I've got this little file or program I called NBN complete. Now watch this. We'll say our first step is to get the text and convert it into a number. Right? So we'll call up that program. The next step we had was get that number and turn it into a binary. So we created a list of numbers and we'll get that and convert, oh, not read binary, I want to, that's further on, decimal to binary was that program, and then the next step is to send it. So I've put those chunks together so that then the students can run one program. So watch this, NBN complete. That would be kind of nice if it was, wouldn't it? Sorry, I shouldn't say that. So NBN complete. So I'll press enter and let's put in Low for Jim's surname. And there's a little LED on my desk flashing furiously off and on. It's now done. And I just, so that people could see, it was producing all these ones and noughts. Every time it produced a 1, that little LED on my desk went flashing on. So you can see, all it does is run all 3 programs, one after another. There's Jim Lowe, there's his name converted into numbers, and then there's all the noughts and ones that combine to his name. So we've finished the first half. We're going to run out of time for the second half. However, the second half is actually a lot harder. I know that sounds weird. The hardest section is this bit here. So our light-dependent resistor, it just reads numbers based on how much resistance it has and how much light is falling on it. The other thing it does, and I can see I've missed a parenthesis on that augment command, which I'll fix up later, is that brightness can vary. It's something called pulse width modulation, but I won't go into that here. But a good way to do it is actually average off that brightness. So read it a couple of times or take the maximum brightness off, which is what I've done, because when the LED is actually off, it's clearly off. But when it's on, you can still get a bit of variation in the brightness. So I said, well, I'll take that maximum brightness out of there. It's temp, not for temporary, but short for temporary. So there's my little routine that picks up and says, well, how bright is this little LED? And I'll strip off the brightest one, and then I'll make decisions on calling that a 1 or a 0. And that's where the problem starts. All right? So we've got our 1s and 0s. But here's the question marks for us. Our receiving device theoretically does not know the size of the message that it's about to receive. So how does it know when to start reading and when to stop reading? So somehow we need to communicate something about the length of the message so that it's not still sitting there waiting. If you go back to the Ascii code at the start, there is a sort of a clue where there's a number 2 says start of text, and if you send the number 3, then that's the end of a text. Or number 4, end of transmission, because you might have other stuff attached to it. So the Ascii code actually included stuff to help us identify when a message was being initiated and when it was being finalized. The next problem, how fast is data being transmitted? How do we know when to read the LED? Do we know that 2 1s was 2 ons, or was it really just one long 1? I know that might sound weird. And the solution is something called synchronous and asynchronous data. Synchronous means there's a clock pulse, So when the clock goes high, in other words, you have 2 LEDs on the circuit. One's a clock pulse just going on and off. Every time the clock goes on, you read the signal. The downside about that is now you're using up 2 signals down our transmission cable. So there's another system called Asynchronous Data where you put the time circuit at the start, tells you how fast to read the data. So they're the 2 different systems in place. Yeah.
It sounds like there's so much more. Perhaps we need STEM 2 to follow this one because we're getting tight on time here.
Yep. So what about data validation? That's where they talk about parity bits. And that is the end of it because at least we've got through how to send the information and the sorts of problem solving, which is key to any STEM course, is having the students think they can get into this, and then when they start the receiving part, they realise how much is in a data communications engineer's job in making sure that we can get this data, and put it back that we're sending this at a frequency of about 10 hertz, whereas your computers are running at gigahertz. That's pretty scary. So that is the end from me. So I managed to get there 2 minutes over time. I apologise. So I'll go back to you then, John.
Thanks, Peter. And I was just thinking about that if people have questions that they want to ask, obviously they can watch it on demand, both on their website and also via the YouTube channel. But perhaps they could send you some questions as well if they have questions that they want to ask.
Yep, certainly, and they would have seen, just flick up on the screen for a second there, that there's the STEM activities on our website, and that binary one is one of them that's in there, so that they can easily go back and practice those with their students, and of course they'll have access to that PowerPoint and the TNS files to experiment.
Great. And like you said, it is just, let's just have a go, isn't it? Just have an experiment, and you can see from what you found there, you start thinking one thing and it just grows and grows, and what if, and I found that in the classroom, that you don't actually have to do too much yourself. The kids want to go off and find all these things, and it really takes, like you talked about the flipped classes, it takes the pressure off us as teachers.
It does, but it means we need to have all those resources at hand, and it is one thing I like about the Innovator is it's got so much flexibility in it that they can go off and teach themselves on the website, because there's 10 minutes of code for Innovator.
Great.
And I think,
thank
John
you very much.
And Peter, just a quick comment that, I think what we showed is 2 very different activities, one quite simple, one with enormous potential to get into all sorts of further investigations, but both essentially using the same technology, simply turning an LED on and off. So even a very simple first step in STEM to incorporate something new into your classroom, and you've got a whole lot of more activities that you can build on.
That's right, Jim. And I don't think there's one student that I've seen, or an equally teacher that I've showed that, just the LED blinking, who hasn't looked at that and gone, that is so cool. And it's so simple. That's just the start. That's literally the tip of the iceberg, and yet they get so much feedback from that and so much pleasure. They want to learn more. So that's cool. Thanks, Jim. Well, thank you very much, both of you. When tonight's webinar does finish, there will be a brief survey. It will automatically appear in your browser, and your feedback does guide us as we plan future online events. We do listen to your feedback, and so we hope you do share your thoughts in a post-webinar survey. Importantly, your certificate of attendance will be emailed to you in the next 48 hours, along with the link, like I said, to the on-demand and YouTube versions of the recordings, as well as any relevant documents. If you want to watch it again, to recap a few things, you want to get some resources from that, and equally share it with your peers. After we leave tonight, if you do have any post-webinar follow-up that you want to, you can by all means phone either of those 2 numbers or email teacher support. I know that Peter regularly is on those calls as well, so I'm sure that he would love to talk to you more about it and share his resources with you on top of the ones that are on the on-demand. And sadly, that brings us to the end of tonight's webinar. Thank you very much, Jim and Peter, for everything you've shared tonight.
You're welcome.
Thanks, John. Enjoyed it. Hope everybody else did too.
Yeah, well, I certainly did, and I'm sure the participants did. There was some nice feedback in the chat window, so thank you for that. And equally, thank you, participants, for joining us this evening, and we hope to see you back online soon. So thank you all, and good night.